Why does methanol dissolve in water but oil does not? Simply put, like dissolves like. That is, compounds with similar intermolecular forces will mix with each other. Let's look at the dissolution of methanol into water. Shown in the animation is methanol and water with a phase boundary between them. The hydrogen bonds are shown with dashed lines, and in reality the water and methanol molecules will be moving within themselves. The hydrogen bonds would be constantly breaking and reforming as the molecules move in the solution. To simplify the animation, the molecules are stationary. When water and methanol mix, a methanol molecule would be transferred from the methanol phase into the water phase, or a water molecule would be transferred from the water phase into the methanol phase. Both would occur because this is an equilibrium process across the phase boundary. But let's only consider the transfer of a methanol molecule into the water phase. First, intermolecular bonds around a methanol molecule must be broken. This requires energy and is an endothermic process. Now consider water. Some hydrogen bonds must be broken to create a cavity in which the methanol molecule can fit into. Again, this requires energy and is an endothermic reaction. Next, transfer a methanol molecule into the water phase. There would be little or no bonding interaction between the nonpolar methyl group and water. However, since both molecules can hydrogen bond, strong hydrogen bonds will form between the methanol and water. This bond formation is favorable and is an exothermic process. Methanol is miscible in water, which means it is soluble in any proportion. The dissolution process continues until there is only one liquid phase. Hydrogen bonds are constantly switching between water and methanol molecules, and the methanol and water molecules are free to mix with each other because of their similar intermolecular bonding interactions. Thus, there is only a small change in entropy or disorder of the system when mixing occurs. Let's now consider the dissolution of hexane into water. The intermolecular forces between hexane molecules are weak hydrophobic interactions, and since there are no hydrogens bonded to electronegative atoms, hexane is unable to form hydrogen bonds. The intermolecular forces between water and hexane are therefore very different. Let's go through the same thought process again. Weak hydrophobic bonds, or London dispersion forces, must be broken between the nonpolar hexane molecules, and strong hydrogen bonds between water molecules must be broken in order to form a cage that the hexane molecule will fit into. After the insertion of hexane into the cage of water molecules, we see that little if any bond formation would occur between hexane and the water molecules. Also notice that the system has lost entropy and has become more ordered with a rigid cage of water molecules surrounding the hexane molecule. This is an unfavorable process because of the loss in entropy. Now consider another hexane molecule dissolving into the water phase. Shown in the animation are 8 water molecules that are surrounding each hexane molecule for a total of 16. What would happen if 2 hexane molecules coalesced? Now 10 water molecules are needed to surround both hexane molecules. Thus, the ordered cage structure is minimized by the aggregation of both nonpolar molecules with each other. The system will change as to minimize entropy or disorder. Even though the hexane molecules are more ordered when combined, the increase in disorder of the water molecules that become freed from the cage structure is so great that the entropy of the system is greater when the hexane molecules coalesced. Thus, when hexane is added to water, 2 phases will form. However, there is some partial solubility of hexane in water, and water into hexane. Now consider mixing 2 hydrocarbons such as hexane and pentane. Both molecules do not contain polar functional groups, and only weak dispersion forces exist between their molecules. Let's go through the same thought process again. When a nonpolar pentane molecule moves into the nonpolar hexane molecules, hydrophobic or London dispersion intermolecular forces are disrupted between the hexane molecules, but new dispersion forces are formed between hexane and pentane molecules. The dissolution of pentane into hexane, or hexane into pentane, continues until there is one liquid. Notice that the structure of the solution and the strengths of the attractions between the molecules are very similar to the structure and attractions found in the separate pure liquids. Thus, the freedom of movement of pentane and hexane is about the same as the freedom of movement in the pure liquids. Therefore, when very similar liquids, like pentane and hexane, are mixed, the natural tendency towards increasing entropy drives the process to form one phase. Like dissolves like. Compounds that are polar will dissolve in polar solvents. Compounds that are slightly soluble will dissolve in slightly polar solvents. And nonpolar compounds will dissolve in nonpolar solvents. For fun, let's consider 2 alcohols and their solubility in water. What is more water soluble, 1-butyl alcohol or tertiary butyl alcohol? Let's consider the equilibrium across the phase boundary between the liquids, and to make it less complicated, let's only consider the entropy changes for each system when one solute molecule is transported into the water phase. Notice how it takes less water molecules to form a cage around tertiary butyl alcohol than one butyl alcohol. The unfavorable entropy change for the dissolution of tertiary butyl alcohol is less than for one butyl alcohol. Thus, we would expect the solubility of tertiary butyl alcohol to be greater than one butyl alcohol. And in fact, tertiary butyl alcohol is miscible in water, whereas one butyl alcohol is only partially soluble in water. Its solubility is 80 grams per liter. The dissolution of a solute into a solvent is a complex thermodynamic process in which we should be considering both the enthalpy and entropy changes of the system when dissolution occurs. But hopefully through this animation, we have given you some insight into the meaning of the phrase, like dissolves like.